You think nature loves smooth shapes? Look around you. Look at the world you live in. What do you actually see? Circles, spheres, perfect straight lines, smooth curves that flow without interruption. That's what your textbooks show you. That's what your geometry classes taught you. Circles and squares, triangles and rectangles, spheres and cubes and cones, beautiful, smooth, perfect shapes with clean edges and simple formulas. But step outside, look at a cloud. Is it a sphere? Look at a mountain. Is it a cone? Look at a coastline. Is it a curve you could draw with a compass? No, none of them, not even close. Nature hates smooth. Nature produces rough. Nature creates jagged, irregular, complex shapes that that your geometry teacher never mentioned. And here's the strange part. For over 2,000 years, mathematicians pretended this wasn't true. Let me show you what I mean. Euclidean geometry is one of humanity's greatest intellectual achievements. Around 300 BC, the Euclid compiled the geometric knowledge of the ancient world into a systematic framework. Points, lines, planes, circles, triangles, polygons, axioms, theorems, proofs. A beautiful logical structure that has been taught in schools ever since. And it works. It works brilliantly for certain things. If you want to build a house, Euclidean geometry tells you how. If you want to survey land, calculate areas, design machines, navigate by the stars. Euclidean geometry is your tool. It's precise, it's powerful, it's been tested for millennia. But Euclidean geometry has a hidden assumption, an assumption so deeply embedded that most people never notice it. The assumption is that the shapes worth studying are smooth shapes, shapes with clean boundaries, shapes that simplify when you look closer. Think about a circle. From far away, it looks like a circle. Zoom in on the edge. What do you see? A curved line? Zoom in more. The curve looks straighter. Zoom in enough, and the circle's edge becomes indistinguishable from a straight line. This is the foundation of calculus. At small enough scales, curves become straight. Complexity becomes simplicity, roughness becomes smoothness. This works for circles. It works for spheres and ellipses and parabolas. It works for all the shapes that Euclid studied and all the shapes that calculus was built to handle. But it doesn't work for nature. Look at a coastline. From space, it has a certain shape. Zoom into the scale of a country. More detail appears. Bays and peninsulas you couldn't see before. Zoom in to the scale of a city. More detail, inlets and headlands. Zoom in to the scale of a beach. More detail. Rocks and tide pools. Zoom in to the scale of a single rock. More detail, pits and crevices. At what point does the coastline become smooth? At what scale does the complexity disappear? Never. The coastline never becomes smooth. No matter how closely you look, there's always more detail, more roughness, more irregularity. The coastline refuses to simplify. This is fundamentally different from Euclidean shapes. And it's not just coastlines. Look at a mountain. The silhouette is jagged. Zoom in on any section, still jagged. Zoom in more, and smaller peaks and valleys appear within the larger ones. The roughness persists at every scale. The mountain never becomes a smooth cone, no matter how closely you examine it. Look at a cloud. The boundary is complex, turbulent, ever-changing. Zoom in, and you see smaller wisps and billows. The complexity doesn't disappear. It transforms into different complexity at smaller scales. Look at a tree. The branching pattern, the texture of bark, the edges of leaves, rough at every scale you care to examine. look at a river system from above, the main river with its tributaries, each tributary with smaller tributaries, each smaller tributary with streams feeding it. The pattern repeats and repeats, never resolving into smooth channels. Look at your own body. The surface of your lungs folded and refolded to maximize surface area. The convolutions of your brain, the branching of your blood vessels, rough structures serving biological functions precisely because they are rough. This is the world we actually live in, not the world of circles and spheres and smooth curves, the world of roughness, the world of irregularity, the world of shapes that refuse to simplify no matter how closely you look. And for over 2,000 years, mathematics had almost nothing to say about this world. I found this astonishing. Here we have the dominant geometry of Western civilization, a geometry that claims to describe shape and space, and it cannot describe the shapes that actually exist in nature. Clouds are not spheres, mountains are not cones, coastlines are not circles, lightning does not travel in straight lines, the bark of a tree is not smooth. Euclid's geometry is a geometry of the artificial, the manufactured, the designed. It describes the shapes that humans create, buildings, machines, tools, roads. It describes the idealized shapes that humans imagine, perfect circles, exact squares, infinite planes. But nature doesn't work that way. Nature doesn't smooth things out. Nature doesn't simplify. Nature creates complexity at every scale. Nature hates smooth. Why? What is it about natural processes that produces roughness instead of smoothness? The answer lies in how natural shapes are created. Consider how a coastline forms. Waves crash against rock, the rock erodes, but it doesn't erode uniformly. Some rock is harder than other rock. Some angles of wave attack are more effective than others. Weather varies, tides vary. The process is inherently irregular. And here's the key. The irregularity at large scales creates irregularity at smaller scales. A large bay forms because a soft rock formation eroded faster than the surrounding hard rock. But within that bay, the same process operates at smaller scales. Softer patches erode into smaller inlets. Harder patches remain as smaller headlands. The irregularity cascades down through the scales. This is why coastlines are rough at every magnification. The same irregular erosion process operates at every scale. The cause of large-scale roughness is the same as the cause of small-scale roughness. The pattern propagates through the scales. Mountains form the same way. Geological forces push rock upward, but the pushing isn't uniform. Fault lines create discontinuities. Different rock types respond differently. Erosion attacks the uplifted rock, but erosion itself is irregular. Rain falls unevenly. Rivers cut channels that depend on minor variations in initial conditions. The roughness at large scales creates the conditions for roughness at smaller scales. Clouds form through turbulent mixing of air masses. But turbulence is inherently irregular at every scale. Large eddies contain smaller eddies. Smaller eddies contain smaller eddies still. The turbulence creates structure at every scale, and that structure is rough, not smooth. Trees branch because branching is an efficient solution to the problem of filling space with leaves while maintaining transport from a single trunk. But the branching process introduces irregularity at every level. Each branch is slightly different. Each sub-branch responds to local conditions. The pattern is similar across scales, but never identical. In every case, the roughness isn't a failure of the shape to be smooth. The roughness is the shape. The irregularity isn't noise to be filtered out. The irregularity is the signal. This is what I spent my career trying to understand. Not the smooth shapes of Euclid, but the rough shapes of nature. not the geometry of idealization, but the geometry of reality. And I discovered something remarkable. These rough shapes, despite their apparent chaos, have structure, they have patterns, they have mathematical properties that can be measured and compared and understood. The key insight is scale. Euclidean shapes have characteristic sizes. A circle has a radius, a square has a side length. These measurements are absolute. They don't depend on how you look at the shape, but rough shapes don't work that way. The measurement of a rough shape depends on the scale at which you measure it. Consider the coastline problem. How long is the coastline of Britain? This seems like a simple question with a definite answer, but it's not. If you measure the coastline with a ruler 100 kilometers long, you get one answer. You're skipping over all the bays and peninsulas smaller than 100 kilometers. Your measurement captures only the large scale shape. If you measure with a ruler 10 kilometers long, you get a larger answer. Now you're capturing more of the indentations. More detail means more length. If you measure with a ruler 1 kilometer long, larger still, even more detail captured, even more length measured. The smaller your ruler, the longer the coastline becomes. There is no true length of the coastline of Britain. The length depends on the scale of measurement. This seems paradoxical until you understand what's happening. In Euclidean geometry, length is well defined because shapes are smooth. Zoom in enough and the curve becomes straight, so you can measure it precisely. But coastlines aren't smooth at any scale. There's always more detail to capture. Smaller rulers always find more length hiding in smaller indentations. The measurement never converges to a final answer. This isn't a measurement problem. This isn't a failure of our instruments. This is a fundamental property of rough shapes. Their length, their area, their fundamental measurements depend on the scale at which you examine them. I called this property fractal, from the Latin fractus, meaning broken or fragmented. Fractal shapes are shapes whose measurements depend on scale. Shapes with roughness at every magnification. Shapes that refuse to simplify when you zoom in. And I developed a new kind of measurement for these shapes. Not length, which depends on scale, but a quantity that captures how length changes with scale. This quantity I called fractal dimension. Think about what dimension means in Euclidean geometry. A line is one-dimensional. It has length but no width. A plane is two-dimensional. It has length and width but no depth. A volume is three-dimensional. But what about a coastline? It's more than a simple line because it's so convoluted that it partially fills a plane, but it's less than a plane because it doesn't actually cover an area. The coastline exists between dimensions. It might have a dimension of 1.2 or 1.3, more than a line, less than a plane. A fractional dimension, a fractal dimension. This dimension is not arbitrary. It's measurable. It tells you exactly how the length of the coastline increases as your measuring ruler gets smaller. It quantifies the roughness. It captures in a single number how the shape fills space across scales. Different coastlines have different fractal dimensions. A relatively smooth coastline like South Africa has a lower fractal dimension than a highly indented coastline like Norway. The dimension captures real geometric information about the shape. And here's the profound discovery. Natural shapes cluster around characteristic fractal dimensions. Coastlines tend to have dimensions around 1.2 to 1.3. Mountain profiles have dimensions around 1.2 to 1.4. Cloud boundaries have dimensions that reflect the turbulent processes that created them. The fractal dimension is a fingerprint of the process that created the shape. Measure the dimension and you learn something about the underlying dynamics. Different processes produce different roughness. The mathematics captures this. Now you might ask, why does this matter? Why should anyone care about the geometry of roughness? We've built civilization using Euclidean geometry. It seems to work fine. Why do we need anything else? Because the smooth approximation hides reality. When engineers design structures, they typically assume smooth surfaces and simple shapes. But real materials aren't smooth. Real surfaces have roughness at every scale. And that roughness affects how structures behave. Fractures in materials follow rough paths. The roughness of the fracture surface tells you about the material's properties. Understanding that roughness helps you predict failure. Fluid flow over rough surfaces behaves differently than flow over smooth surfaces. The roughness affects drag, turbulence, heat transfer. Ignoring roughness means getting the physics wrong. Electrical signals in rough conductors propagate differently than in smooth conductors. The geometry matters for electronics and communication systems. Medical imaging reveals rough structures in the body. The fractal dimension of blood vessel networks changes with disease. The roughness of lung tissue reflects health or pathology. Understanding these rough geometries has diagnostic value. Financial markets produce rough time series. Prices fluctuate with irregular patterns that persist across time scales. The roughness of market data reveals information about risk that smooth models miss entirely. In every case, treating rough things as smooth loses information. Sometimes the lost information doesn't matter, but often it does. The roughness is telling you something real about the system. Ignoring it means ignoring reality. This is why I spent decades arguing for a new geometry, not to replace Euclid, but to complement him. Euclidean geometry for smooth shapes, fractal geometry for rough shapes. Together, they can describe the full range of forms that exist in the world. Let me return to where I started. Nature hates smooth. Why? Because smoothness requires effort. Smoothness requires processes that actively remove irregularities. Smoothness requires equilibrium. When you polish a surface, you're applying a smoothing process. You're abrading away the rough spots. You're creating uniformity through deliberate action. Stop polishing and the smoothness begins to degrade. Dust accumulates, corrosion attacks, the surface roughens again. When water sits perfectly still in a container, its surface is smooth. But introduce any disturbance, any flow, any energy, and waves form, ripples and eddies. Roughness emerges spontaneously. Smooth shapes are special cases. They require special conditions. They are the exception, not the rule. Natural processes are not smooth. They're driven, they're turbulent, they're variable. They operate differently at different scales. They produce roughness naturally because roughness is the generic outcome. The sphere is special. It minimizes surface area for a given volume. But achieving a sphere requires special conditions. Surface tension in a raindrop, gravitational equilibrium in a planet. Without those special conditions, you don't get spheres, you get irregular lumps. The straight line is special. It's the shortest path between 2 points, but achieving a straight line requires special conditions. A beam of light in vacuum, a string pulled taut. Without those conditions, paths curve and wander and roughen. Classical geometry captures the special cases, the idealized shapes that emerge under special conditions. But nature mostly doesn't operate under those special conditions. Nature operates in the rough. Here's what I want you to understand. For 2,000 years, geometry was the study of smooth shapes. And for 2,000 years, we tacitly assumed that smooth shapes were fundamental and rough shapes were deviations. Roughness was noise. Irregularity was error. The real shape was hiding underneath the roughness, waiting to be revealed by better measurement. This is exactly backwards. Roughness is fundamental. Smoothness is the deviation. The real shape is the rough shape. Smoothness is what you get under special conditions that suppress the natural roughness. When you look at a cloud and see irregular billows instead of a perfect sphere, you're not seeing a sphere obscured by noise. You're seeing the actual geometry of turbulent mixing. The irregularity is the shape. When you look at a coastline and see bays and peninsulas and inlets, you're not seeing a circle distorted by erosion. You're seeing the actual geometry of geological processes. The roughness is real. When you look at a mountain and see jagged peaks instead of a smooth cone, you're not seeing a cone disrupted by weathering. You're seeing the actual geometry of tectonic forces and erosion. The roughness is the mountain. Fractal geometry doesn't smooth away the roughness to find a hidden simple shape. Fractal geometry embraces the roughness. It provides tools to measure roughness, classify roughness, understand roughness. It takes the irregular world seriously, and in doing so, it opens new windows on reality. The fractal dimension of a shape tells you about the process that created it. The scaling properties of a system reveal its underlying dynamics. The roughness that Euclidean geometry ignores is often the most informative feature of a system. Classical mathematics gave us tools for the ideal. Fractal mathematics gives us tools for the real. Classical geometry taught us to see smooth shapes everywhere, even where they don't exist. It trained us to ignore roughness, to see it as imperfection rather than information. Fractal geometry teaches us to see the roughness, to recognize that irregular shapes are not failed smooth shapes, they are successful rough shapes. They are the geometry of nature. I didn't invent roughness. Roughness was always there. I just gave it a mathematics, a language to describe it, a way to measure it, a framework to understand it. And once you have that mathematics, once you see the world through fractal eyes, you can never go back to seeing only smooth shapes. You see roughness everywhere because roughness is everywhere. You see patterns in the irregularity because the irregularity has patterns. You see structure in what everyone else calls chaos because the structure was always there waiting to be recognized. Nature hates smooth because nature is rough. The smooth shapes of Euclid are human constructions, human idealizations, human simplifications. They are useful fictions for building and designing and calculating, but they are not the shapes of the natural world. The shapes of the natural world are fractal, rough at every scale, complex beyond simple description, but not beyond description altogether. Fractal geometry describes them. Fractal dimension measures them. Fractal thinking understands them. This is my case against Euclidean intuition. Not that Euclid was wrong, but that Euclid was incomplete. His geometry captures one kind of shape, the smooth kind, the ideal kind, the rare kind, the other kind, the rough kind, the natural kind, the common kind that required new mathematics. Mathematics I spent my life developing, mathematics that finally gives us tools adequate to the rough world we actually inhabit. Clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, lightning is not straight. Nature hates smooth, and mathematics should too. Not comfort, not idealization, truth,